Alrighty, guys. Today we're going to talk about page 34, which is about Gay-Lussac and Avogadro. These are the names of scientists who discovered these fun gas law equations. Kind of some funny names, but it was a long time ago. So there's that. Let's zoom in a little bit. Okay, first guy, Gay-Lussac. What did he come up with? He came up with the one that has to do with pressure and temperature. Okay, so when volume is held constant, the pressure and temperature of a gas are directly related. We talked about this on Monday or Tuesday, whenever day one was. Okay, they're directly related. So remember to convert to Kelvin. Remember, whenever we have temperature in a gas law equation, we always want to convert to Kelvin. Only Kelvin is allowed to plug in. Okay. Okay, so let's look at this cute little picture. It says the pressure exerted of a gas is directly related to the Kelvin temperature. Okay, so here you can see there's like a little flame and a few arrows. And then when the flame gets bigger, there's more arrows showing, oh, there's more collisions. There's going to be more collisions when temperature increases. Okay, so when temperature goes up, pressure is going to go up and vice versa. Okay, so let's remind ourselves, what kind of units can we have for pressure? We can have atmospheres for pressure, we can have kPa, we can have psi, we can have millimeters of mercury, we can have torr. I think that might be it. Okay, what can we have for temperature? In the problem, we can see degrees Celsius, we can see Kelvin, but whenever we're plugging something in to the equation, we have to convert to Kelvin first, even if it's given in Celsius in the problem. Okay, so let's look at an example. This example says, determine the pressure change when a constant volume of a gas at 1 atmosphere is heated from 20 degrees Celsius to 30 degrees Celsius. Okay, so here is our pressure. Here's our first pressure. So let's label it P1. Okay, and I know that's pressure because it's an ATM, right? ATM is pressure. Okay, it's heated from 20 degrees Celsius. Okay, so this is going to be a temperature, and this is also going to be a temperature. This is my first temperature, this is my second temperature. Okay, before I can plug anything in with temperature, I have to convert to Kelvin. So let's make a note to ourselves, plus 273. That's how you convert to Kelvin. So we're going to do 20 plus 273, and I get 293. Let's write that down. That's 293 Kelvin. And then this one, I'm going to go 30 plus 273, and I get 303. So this one's going to be 303 Kelvin. Okay. Okay, so pressure and temperature. So I'm going to be using Gay-Lussac's law, which is P1 over T1 equals P2 over T2. Okay. And let's see here. So let's plug stuff in. I've got P1 over T1, 293 Kelvin, equals P2, which is what I'm solving for. So that's going to be my variable. That's like my X or whatever, over T2, which is 303 Kelvin. Okay, so now I need to solve. Now, if you remember the little shortcut I told you last time, whenever you have a little proportion like this, you need to solve it. Find the two that are across from each other, and you're going to multiply those. So cross, remember I called it the cross and box method. So you're going to cross multiply the two that are across from each other, and then divide by whatever's left over, divide by the box. So let's do that. Just cross multiplying and dividing. So I'm going to go 1.00 times 303, and then I'm going to divide by 293. Okay, and that's what I get for P2. So I'm going to round that. So P2 is equal to 1.034129, which is, if we have 3 sig figs, it's going to be 1.03. And what are my units? What are my units? ATM, because the first pressure was in atmospheres, the second pressure must be in atmospheres. Okay, but hold on. What's the question ask? Determine the pressure change. So did it change by this much? No, the final pressure was this much, but how much did it change? So what's the change in pressure? So the change in pressure is going to be my 1.03 minus my 1.00. So my final pressure minus my initial pressure, and that gives me 0.03 atmospheres. Okay, so that would be my answer. So just make sure you read the question, and you had to solve for the final pressure so that you could figure out how much it changed from beginning to end. Okay? Okay. And then the sig figs get weird because technically when you're multiplying and dividing, you got to maintain sig figs. Then when you subtract, it gets a little fuzzy because if you guys remember, the rules for addition and subtraction have to do with decimal places, not sig figs, because these had 2 decimal places. This can only have 2 decimal places. So it gets a little fuzzy there when we add in addition and subtraction. But that's correct. So kind of weird, I know. Okay, next one's Avogadro's principle. We've heard of Avogadro before. He's got a kind of a funny name. It sounds like avocado. He's the guy who came up with the mole, which is handy because this has to do with moles, okay? This has to do with moles. Okay, so for an ideal gas, the volume and amount of gas, and by saying amount of gas, you're really talking about the moles of gas, because remember, we count things that are really tiny in moles, because things that are super tiny, like atoms and particles and gas particles, they're so small, we got to count them in moles, just like we count eggs in dozens, because you usually don't just need one egg, you usually need like a bunch of eggs. So we count atoms or gas particles in moles. So the amount of gas and the volume are directly proportional as well. Okay, so that means if your number of moles increases, your volume increases, which makes sense. Think about blowing up a balloon. If I'm putting more air particles into the balloon, meaning I'm increasing the number of moles in the balloon, the volume of the balloon is gonna get bigger. Okay, so here's a nice little picture. This is Avogadro. He's a good-looking guy, right? The balloons all have the same volume. So these guys all have the same volume. Therefore, they must all contain the same number of molecules. Okay, so that's a direct relationship. Let's remind ourselves what units we can see here for volume. We could see liters, we could see milliliters, we could see centimeters cubed. You could see other weird stuff, potentially like decimeters cubed or something, but you probably won't. What does N stand for? N stands for moles. Okay, number of moles. That's it. Okay, so let's do this example. It says if 0.56 moles of helium occupies 11 liters, then how many moles must be added to inflate the balloon to 18.5 liters? So this is moles, so this would be N1. This is liters, so that must be volume, so it's gonna be V1. And it wants to know how many moles must be added, so we gotta solve for N2, that's what we're looking for. And then this one is V2, because liters is volume. So let's write our equation. V1 over N1 equals V2 over N2. Okay, cool. So let's plug everything in. V1 is 11 liters. N1 is 0.56 moles. V2 is 18.5 liters. And N2 is what we're looking for here. That's my variable. So if you remember, whenever we have this situation, I feel like I'm way too zoomed out. Sorry for those of you in the cheap seats in the back who can't see. Okay, so if you remember, what's my secret method? Find the two numbers that are across from each other, cross multiply, and then divide by whatever you have left over here. Okay, so I'm gonna go, oh, now I'm like too zoomed in. I'm gonna go my 0.56 times my 18.5, enter. Then I'm gonna divide by my 11, enter. And this is what I get. So N2 is equal to 0.941818, etc. So how many sig figs do I need? It looks like I need 2 sig figs. Zoom out a little bit. Looks like I need 2 sig figs. So I'm going to go 0.94 moles. Because remember, N stands for number of moles. So that must be my number of moles. Okay, but what's the question ask? It says how many moles must be added? Okay, so if my original moles was 0.56. My ending moles had to be 0.94. How much were added? How much were added? So I'm going to go 0.94 minus 0.56 to figure out how much was added. 0.94 minus 0.56, and I get 0.38. So 0.38 moles added. Okay, so again, make sure you read the question to make sure you understand what it is asking. Okay? Okay, and that's it. Those are the 2 new gas laws we learned today. So, if you go to the back, you have 6 problems to do, very similar to what we did the other day. But for each problem, I want you to write the equation first. I want you to tell me which number is going with which variable. Okay? And then you're going to solve for the unknown. Couple of things, kind of hint here, like even if it gives you Celsius, you still need to convert to Kelvin to plug it into your equation. And then once you're in Kelvin, if you get an answer in Kelvin, but it asks you to solve for it in Celsius, then at the end you convert back to Celsius by subtracting 273. Okay, so just read the hint there. And the other hint I wanted to give you was if it says, I think somewhere on here it says like, right here, standard pressure and standard temperature. Think back to what we learned the other day on page 32. What's standard temperature and what's standard pressure? It's right here on page 32. Okay, standard temperature is 273, standard pressure is 1 atmosphere. Okay, so that's what you can use there where it says standard temperature and pressure. Okay, go ahead and work on that assignment, guys.